All right, welcome to chapter 22 of Earth Science. This is looking at our neighbors in space, looking at our solar system. When we start talking about our solar system, one of the things that we're going to be talking a lot about are planets. Now, in order to talk about a planet, we need to really kind of define what a planet is. And the ancient Greeks gave us the word planet, which literally means wandering star. So you recall in the last chapter, in chapter 21, we noticed how some objects in the sky, these little objects that didn't fit with the rest of the constellations, but they had those retrograde motion, those loop-de-loops that move around across the sky. And so they were literally wandering across the sky, hence the name planet. You may recall in our oceanography chapter, we had the word plankton, same origin. So these wandering planets that are wandering stars that moved across the sky. Now, it wasn't until 2006 that we actually defined what a planet actually is. It is an object in the sky that orbits around the sun, has a significant mass enough for self-gravity to overcome any rigid body forces that assume are going to make it a sphere or nearly round shape, and it has cleared out its own orbit. And again, that wasn't until 2006, which did not bode well for the status of Pluto as a planet. Pluto, by definition, didn't meet that third one. We'll talk more about Pluto and the objects out in this area known as the Kuiper Belt here in just a second. So if I were to ask you, how many planets are there? Well, it's kind of a tricky question. The first one I could answer. I usually have an astute student who, in a traditional class, would say, "Oh, there are thousands of them," and they'd be right. There are over 4,000 exoplanets that have so far been discovered. A lot of them are using the looking at the Kuiper's law, Kepler's law of planetary motion, where objects would move in front of the star. And as they moved in front of the star, we could see how fast they're moving based on Kepler's laws of planetary motion. Then we could figure out how big they are based on how far away they are, or how close they are to the sun based on how much light is being blocked out. And then when we could actually identify the object in its location around these exoplanets, these other stars. But if we stick to our solar system, that still gives us a kind of a tricky question. Now, if I were one of the ancient Greeks, a celestial body that wandered across the sky would be the sun. It's in the sky, and it wanders across the sky. And so would the moon. And so there would have been 7 planets: Saturn, Jupiter, Mars, Mercury, Venus, the sun, and the moon. And those are all objects that we can see without a telescope. So those were the original planets. And we've since Copernicus' time, again, more on that in chapter 21, we had now have a heliocentric view of our solar system, which makes the Earth a planet. You'll notice that the Earth wasn't an original planet, but with making the sun the center of our solar system, a heliocentric view, then the Earth becomes a planet, and the moon also is demoted in that same time as the sun, in that the moon orbits around the Earth and not around the sun. So what year did the IAU officially define, the International Astronomical Union officially define what a planet is in our solar system? That was 2006. And it led to a lot of controversy about, because Pluto isn't officially a planet, Pluto had a lot of fandom here in the United States because it was the only planet that was discovered with a telescope here in the United States. Again, more on Pluto later. So what are all the objects in the solar system besides those planets? Well, after 2006, we have this new category called dwarf planets. We've got moons, comets, asteroids, the other objects out in the Kuiper Belt, the Oort cloud, and also, most importantly, the sun. So when we start looking at this table, this kind of talks about all of the different objects in our solar system. We have one star. Not every star will be isolated. In some cases, we have two stars that will orbit around one another depending on the size of the mass of each one of those. If you're in the lab class, you'll actually get a chance to play around with some of these model simulators that will look at, you can actually make binary stars that go around one another. It's really hard to have planets that are in these binary stars because these planets are going to be pulled by both of those stars. But in our solar system, we have one star, the sun, 8 planets, and we'll talk more about those 8 planets. We've got some dwarf planets, which are not objects that have not cleared out their orbits. We've got 2 orbits that we're going to talk a little bit about. One is the asteroid belt and the other is the Kuiper belt. We've got 181 and counting moons. Some of these moons have enough gravity that they became spheres. Some of these aren't. Some of them are more potato shaped as a result of being so small. And not having enough gravity to cause these things to become a sphere. We've got asteroids, which have eccentric orbits. I mentioned the Kuiper belt. The Oort cloud is a sphere that's in all directions, that is collecting these icy droplets, icy objects that are held in by the sun's gravitational pull, but extending out to about a quarter of the distance to the next nearest star. And so we're talking light years for some of these objects in the Oort cloud. So the other things that we have are comets, which are commonly affectionately called dirty snowballs, and that they will get close enough to the sun that some of the gases some of the gases will burn off and leave behind an ion trail and a dust trail associated with those comets. And then finally, meteoroids, which are objects less than a meter across that orbit the sun. A meteoroid is a object in the sky. It's a meteor when it comes through the atmosphere, and it becomes a meteorite when it if it makes its way to the Earth's surface. So those are all very similar objects. The word meteors, we have meteorology, which literally means from the sky. So here's a diagram that looks at these different objects in our different planets. And so again, by definition, a planet is an object that orbits the sun, is a sphere, and has all of the objects in its orbit cleared out. And so when we start looking at Pluto, it doesn't meet that third criteria. Now, when we start looking at planets like this, you think, wow, Jupiter's really big, especially compared to Earth. And it is compared to Earth. And that's the key term. But when we start looking at our solar system, 99.85% of our solar system is the sun. So that remaining fraction of a percent is all the other stuff, including our planets. Now, Pluto, again, didn't meet those two the third of the 3 criteria for a planet. And so by definition, it's not a planet. And so if you want to know more about this, there's a great book called The Pluto Files, and it talks about how Pluto didn't quite fit in with the terrestrial planets that we'll get into, or didn't fit into the gas giants. And so it just kind of was on its own. And as a result, there's a lot of controversy about a planetarium in New York that only categorized the 4 inner terrestrial planets and the outer gaseous planets. And there wasn't really a place for Pluto. And so as a result, this led to a lot of controversy associated with the demotion of Pluto to a dwarf planet. So other dwarf planets include Ceres, Cynda, and Eris. So when we start looking at the Kuiper belt, there is an objects out around Pluto that Pluto hasn't cleared out its orbit when we start looking at all these objects here. And so here are some of the objects in the Kuiper belt. Again, some of them are larger, some of them are smaller, but in order for Pluto to be a planet, it would have to clear out all of these different objects. So when we start looking at Pluto, it is quite small. It still does have a spherical shape, but if we compare the Earth over here to Pluto, it is small. It is smaller than our moon. It is smaller than multiple moons. So it is very, very small in comparison to some of our other planets. We start looking at some of the other objects in the sky. They're a little bit bigger, but again, when we start looking at Pluto, it is quite small. So we learned a lot about Pluto in 2015, where the New Horizons spacecraft did a flyby, and it took a number of photographs. In fact, the photograph that you're seeing here is from that New Horizons spacecraft as it's moving. And Newton told us an object in motion remains in motion unless acted on by an external force. So it started, the New Horizons spacecraft was shot out over a decade ago now. It took multiple years to make its way to Pluto, and it got close enough to Jupiter to pull in some of the gravitational pull and accelerate. Jupiter rotated or orbited away from New Horizons. It changed its trajectory, and it did its flyby as in 2015. And when it did, it took some amazing photographs. So lots and lots of additional research is still going on. Now, since it's an object in motion and it's continuing in motion, it did its flyby and it's continuing to move in that same direction. So we're throwing it out to the outer portions of our solar system. And so eventually it's going to move beyond the Kuiper belt. So when we start looking at the objects, this is not to scale, but we can see that they're all moving in that same relatively flat surface or plane. And so we call this the plane of ecliptic. And so, again, these are not to scale, but this is a really good diagram that shows that they're all perfectly aligned. So that means that some objects will move in front of us, and we call that a transect. And so we'd actually see a little tiny dot moving across the sky if we saw Venus or Mercury moving at the sun. You should never look directly at the sun, but if you had specialized glasses that you could in fact look at the sun, you would see that little dot moving across the sky if it made its transect. And so you can see in many cases, these planets are all virtually in that same plane of ecliptic. And that plane of ecliptic is in a flat surface. You can see that the moon is slightly inclined. If it weren't inclined, we would have every full moon and new moon, you'd have 2 eclipses. But it's not, and so we only have these occurring periodically. One of the other things I wanted to point out in this diagram here is that the Earth's axis goes from the South Pole to the North Pole, and if we extend that line out, it's always pointing towards Polaris. So as it's rotating around, it's always pointing towards Polaris. And if we measured that angle from the plane of ecliptic to straight perpendicular to the plane of ecliptic, and that perpendicular angle to Polaris, that's at 23.5 degrees. And so that's what we talk about when the Earth is tilted at 23.5 degrees. It's tilted at 23.5 degrees from that plane of ecliptic. Now, when we start looking at these planets, they are not uniformly spaced. This is a diagram from your book showing a soccer ball, and we can see how many yards or yards, approximately a meter, you would be if the edge of this field was the surface of the sun. And so you could see that we would be about 3 yards away from the sun, and Mercury is about 1 yard comparatively. Venus would be about 2 yards. But then we start getting significantly further. We start looking at Mars being 5 yards. And then there's a big jump between Mars and Jupiter, 17, 20, 32, 63, and then 100. So when we start looking at the difference between these planets, there's clear cutoff in between Mars and Jupiter. I know in lab we're already going to mention astronomical unit, which is the distance from the Earth to the Sun is 1 unit, 1 astronomical unit, and so we can see those size comparisons instead of having to deal with miles or meters. Now, a couple of other things that we have here, one of which is the duration of the day, and these are in Earth days. How long does it take to rotate on its axis? And so you can see that the Earth spins on its axis about every day. The day is approximately the same on Mars. But if we take a look at something like Venus, it rotates exceptionally slow. Mercury, 59 days to make 1 spin on its axis, to make 1 Earth day is 59 days. The duration of its year is how long does it take to move 1 lap around the sun. And so that's what when we start looking at years, and again, that's comparing it to Earth days. Some other interesting things, Venus is actually not rotating like all the other objects in this counterclockwise fashion when viewed from the North Pole. There's 2 hypotheses when we start looking at Venus. One is that the North Pole and the South Pole have flipped, and where literally the planet is flipped over, in which case it would be moving in a clockwise fashion as opposed to a counterclockwise fashion. So that's one hypothesis. The other hypothesis as to why Venus is moving in the opposite direction compared to all the other planets is that the tidal forces associated with this, in our chapter on oceanography, we mentioned tides and tidal locking. And there's a hypothesis out there that the tidal locking is actually occurring on Venus, and it has actually pulled Venus to be tidally locked. And then the force of the other planets pulling on it actually is causing it to rotate the other direction. Again, more information. I wish in a science class I knew all of the answers, but that's the discovery of science, that we in many cases have more questions than answers. And so this is one of those more questions than answers as to why that occurs. We definitely know Mercury is so close to the sun that any moon orbiting around it would get pulled into the sun. And so Mercury is just way too close to the sun. Venus isn't too close. And so why doesn't Venus have a moon? Well, again, one of those mysteries that we have yet to figure out yet. We talked about the Earth having its 1 moon, and it's a response to a collision breaking off a portion of the Earth. Again, we've already talked about that in our early chapters. Mars has 2 captured asteroids, and we can look at the rotation of these asteroid captured objects, and Phobos and Deimos. Then we start getting into those outer planets, those gas giants, and we'll talk more about these. And we can see there's lots of moons associated with these objects. And the masses of these different objects, again, how massive it is compared to the Earth. You can see Venus and Earth are almost identical, both in radius and in mass. And so it's many times it's been considered, Earth and Venus have been considered twins. Relatively same distance. Some of the big differences we'll get into when we look at the planet Venus. So most of the planets in the solar system let's see, are they orbiting planes that lie within 3 degrees? Yeah. Are they orbiting planes that lie within 3 degrees of the Earth's orbital plane? Orbital planes that lie within 3 degrees of the Earth's orbital plane. The Earth's orbital plane, again, is at 23.5 degrees, so no. What about prograde motion? Again, moving in the same direction. Well, that's true for most of them, again, Venus being the one exception. And so the answer would be A and C. So when we started mentioning those prograde and retrograde, we can see that the oddball out there is Venus, that it's rotating in the opposite direction. And so if we flipped Mercury or Venus over, it would be moving in the right direction. And that's what that 177 degrees are. Now, in the lab that we did earlier, for those of you in the lab class, we did a lab that was looking at seasons, and it was talking about the tilt of the Earth was really, really important for causing variation in seasons. And so if you don't have a tilt, you wouldn't have variations in season. And so places like Mercury and Jupiter would have virtually no seasons. Now, again, the Earth is 23.5 degrees tilted, so it would have about this, and Mars is really close. But when we compare it to Uranus, Uranus has a 98-degree tilt associated with it, so it's kind of rolling along its orbit as it moves around. It's rolling around as it moves around its orbit. And so so we can see a varying amount of tilt, which in turn are going to yield a varying amount of seasonality. Now, our closest neighbor in our solar system isn't a planet, it's the moon. And again, we talked about the moon in an earlier chapter that looked at pieces of the material of the moon have pieces of the Earth have broken off to create the moon. And again, if you go back to chapter 2 to look at this, we can see the history of the moon. Now, because the moon is tidally locked, we only see the left image here, which is the face of the moon. Even if it's a full moon, a first quarter, or a third quarter, it's always going to show us that same face because they're tidally locked. Its day is the same as its year. And so the left image is the one that we always see, and that's where we've landed on. However, in 1959, we sent a spacecraft to look at the backside of the moon. Again, it's not the dark side of the moon. In a new moon, when we have no light on our moon shining on the moon that's hitting us, we would actually have the backside of the moon be lit up just as much as a full moon is during a look from our perspective. But again, we're going to see this other side of the moon. Now, on January 3rd, 2019, China actually put on a new, landed a module, a spacecraft to actually land on the backside of the moon. The advantage of being on the backside of the moon is any of the radio waves that we're sending out into space in all directions would be blocked by the moon. And so you'd have perfect way to communicate and pick up any information from outside our solar system without the impedance of the Earth. So you'll notice these dark areas called marias, same word that we get marines, and we thought originally these were seas or dark body or water. We now know that they're lava flows of basaltic lava. The far side of the moon is almost all the highlands. These highly silicate, high amounts of silica-rich materials. The lunar surface has a number of craters, which are pop marking the areas. Since the moon is so much smaller, any plate tectonics is pretty much ended. And so these craters are small enough that they don't have much gas. And so the planet doesn't have much gas. And so without any much atmosphere, these craters are going to be exceptionally cold, because the only way for sun to shine in them would have to be direct sunlight into those craters. And as a result, these craters there's lots of craters that don't get sunlight. And if they don't get sunlight, as a comet goes by, they can pick up little bits of ice. And so some recent discoveries have found that some of these craters have large pockets of ice. Now, anytime a small meteorite hits, the dust and debris would start to build up to form something we call regolith. Now, truly, it's not a lunar soil, because remember, soil has to contain organic materials, and so this is regolith, or broken up bits of rock. And so the image of the footprint on the right is of that regolith. I do want to say that because we don't have an atmosphere to speak of on this object, and we don't have water moving around in that atmosphere, any mark, like a footprint that we make, is going to pretty much stay there until it would get filled in with little micrometeorites. So again, this is a diagram from earlier in the semester where we had a pre-collision, a slightly larger Earth, an object struck the Earth, it sprayed debris into its orbit, that orbit coalesced to form its own moon that we have around the Earth. And we can see in this image that the axis of the moon, or the axis of the Earth, is not the same after the collision. So the Earth's moon, was it formed directly from nuclear fission process immediately following? No. It rotates the same as axis the same as it takes to revolve around the Earth. Yep, that's it. Its atmosphere that burns up most meteorites? No, it doesn't have much atmosphere, so we end up building up some of those meteorites. Those micrometeorites that hit the Earth would burn up in our atmosphere. We don't have an atmosphere on the moon, so the answer is B. So expanding out a little bit further, the Earth and the other objects like Mercury, Venus, and Mars are considered terrestrial planets. The terrain we know is Earth, or land, and so these are land-like or Earth-like planets. And so we can see Venus without any clouds there, and the moon for scale. So the moon and Mars and Mercury are all significantly smaller than Venus and the Earth. So which of these is considered a terrestrial planet? Well, we know Ceres is one of those asteroids, Pluto a dwarf planet, Saturn and Jupiter are gas giants, so it must be Mercury. Oh. So when we start looking at the terrestrial planets, the Earth and all the terrestrial planets, and I will even throw in the moon, are chemically differentiated. Remember that in all of these objects, the heavier iron-rich materials get pushed in towards the center, the less dense rocks that contain more silica are rising up to the surface. So let's kind of go through some of these planets. The first one is Mercury, the innermost planet. The left image is a false color image, heavily cratered surface there. The right is a topographic map showing heavily cratered. Again, no atmosphere to kind of smooth this material off like we have on Earth. Some of the characteristics, the temperature at the equator varies from 427 degrees Celsius during the noon time to negative 173 degrees Kelvin at night. because this wide swing is we have intense sunlight, and in the back, in the areas at night, we would have no atmospheric gases like greenhouse gases and water vapor to hold that heat in. And so you have huge temperature swings. Now, when we start looking at Mercury, it has an abnormally large iron core and magnetic field. There's no active volcanism. Plate tectonics is probably stopped because the planet is so small. There's almost no atmosphere due to the smaller masses. Any materials, any gases in that atmosphere would get sucked into the sun. So we have some visible scarps and faults associated, escarpments with craters. The faults have thought to be resulted from the planet shrinking as it's cooling off. The next planet out is Venus. Now, again, Venus is flipped on its axis, or it's tidally locked and been slowed down and then starting to rotate the other way. Your book talks much more about the first hypothesis, that it's flipped on its axis, so it rotates retrograde, which means it doesn't rotate counterclockwise. If you take that counterclockwise, you can take a ball and rotate it and keep rotating it the same direction. But if you flip it upside down, it's going to move the opposite direction. It rotates very slowly, every 243 Earth days to 1 Venus day. It also has, it orbits, its year is 223 days. So yes, you're reading that right. A year is shorter than a day on Venus. Now, Venus is unusual, even though it is Earth's twin. It has a tremendous amount of carbon dioxide in the atmosphere. And we talked about carbon dioxide as a greenhouse gas. It allows sunlight to move in, doesn't allow heat to get back out. And so the temperature on Venus is 450 degrees, enough to melt lead. And so it's warm. And so if we start looking at Venus, trying to find what the surface of Venus looks like, we have to map with radar, because we've tried twice to go, we as humans have tried twice to go to the surface of Venus, and both times the spacecraft have not survived very long. We've got abundant evidence of volcanism on the planet. And so if the Earth and Venus are so similar, how come they have such different fates? We have the same amount of carbon. Our carbon, however, is trapped in some rocks like limestone, calcium carbon, and oxygen. And so when you hear about greenhouse gases run wild, this is a really good example of this greenhouse gas that is self-perpetuating, because the warmer climate, the warmer environment of the sun, of Venus, is not allowing liquid water to form. And if liquid water doesn't form, then we're not going to be able to trap in some of this carbon dioxide. Without trapping in this carbon dioxide, it's more in the atmosphere, making it warmer. And so this is one of the reasons why Venus is so hot. So here is one of the few images that we do have of Venus. And again, we've only had 2 probes on the surface of Venus, and they both did not last very long. So we can fly over, and using different parts of the electromagnetic spectrum, we can use radar and map the surface. We can fly an orbital object around Venus, and again use radar to map that surface. And so in 1989, the image on the right was made we use radar to measure this three-dimensional map to produce the image of this area. So which of the following does not have any moons? There's only 2 planets that don't have moons. And it's mentioned Mars, we're going to get into as Phobos and Deimos. Pluto is, even though it's so far away, it does in fact have multiple moons. Now Pluto was found in 1920s. It wasn't until the 1970s that we found that Pluto did have, in fact, have 1 moon. And then when we were preparing for the New Horizons, we realized there was multiple other objects. There was actually multiple other moons moving around Pluto. Jupiter, we're going to talk about, has a tremendous amount of moons, as well as Neptune. So Venus would be the only one that we does not have any moons. And again, we don't know exactly why it doesn't. Well, we spent a lot of time looking at the Earth, so we can skip that one and move on to our next terrestrial planet, which is Mars, the red planet. It's cold, dry, covered in rock and dust. It's also significantly smaller, which means the heat would have, from the interior of that planet, would have left earlier, which means could this be the fate of a planet when the plate tectonics subsides, when we lose all of the heat from the interior of our planet? Possibly. Currently, it's cold, dry, covered with rock and dust. Evidence suggests it's warmer and it had liquid water on the surface. We know this because we have large dendritic patterns. If we start looking at the Valles Marineris, we can see some of those dendritic patterns, again, caused by rivers. Mars has a very thin atmosphere. About 0.6% of the atmosphere that we have here on Earth. Like Venus, it's mostly carbon dioxide. Again, the Earth is very unusual that we have our gases, our nitrogen and oxygen with small amounts of carbon dioxide. We have frigid temperatures on the planet. Its day is 24.6 hours, and its seasons are pretty close to the Earth's. And so that means if you were going to be operating one of the Mars rovers that have been driving around on Mars, your day is 24.6 hours. So our days are 24 hours a day. So if you had to go in at the same time every single day on Mars, it'd be 6 hours later, so, or half an hour later. And so half an hour doesn't seem like much, but if you add a half an hour the first day, so if you had to be at work at 8, then 8:30, then 9, a week later, you would get really thrown off. And so if you're willing to study and operate these Mars rovers, it does require you to be on these kind of off-schedule times. Mars has more extreme and longer seasons than we do here because its tilt is slightly more, 23 to 25. The wind speeds, 60-mile-an-hour winds have been reported on Mars. You get these massive dust storms that occur. Because it's 1/10 the Earth's mass, it's going to have 1/4 the gravity. It also has polar ice caps made of dry ice, CO2, that melt in their summer when their pole is tilted towards the sun. So what is the most abundant gas on Mars? It's carbon dioxide. Again, Mars does have, in fact, 2 moons that are probably asteroids captured by Mars's gravity. And again, you can see how much smaller they are, that they're not even fully rounded. Mars has a varied terrain, but it's quite different from the Earth. It's got these highlands and lowlands and volcanic structures, rifts, but no real mountain ranges. Now, main the main hypothesis is why we don't have mountain ranges. We know that we have mountain ranges due to plate tectonics. And so whenever plates come together, it creates those subduction zones and mountains. And if Mars is significantly smaller, that means it cooled off more. Now, Mars does have one hot spot that's still there. That was still there after the plates had already stopped moving. And as a result, it created a huge mountain called Olympus Mons. We can see these canyons left behind by water because it has a dendritic pattern. So here's that Olympus Mons, a huge shield volcano. Remember that as Hawaii is formed through the hot spot, the plate is going to keep on moving. And if the plate is keep on moving, the islands are only going to get so large before the plate shifts and moves away from that hot spot. But if the planet is smaller, they're not going to have plate tectonics. That hot spot is just going to keep on oozing out material in the same place, creating a larger and larger shield volcano. That's why Olympus Mons is the largest volcano found in our solar system and found on Mars. In the last 20 years or so, we've studied Mars pretty extensively. We sent out some rovers. Spirit and Opportunity were the first two that proved the existence of liquid water on Mars. They actually did some mineral identification, found a lot of hematite there, in particular gray hematite, which forms under in water conditions. We have some outflow channels, again, some river deposited materials, some laminate materials that deposited are really effective at sorting out different materials. And so we do know that water was there in the past, but a lot of questions still remain is where did all this water go? Is it in the ground? Is groundwater? Did it get lost into space when plate tectonics stopped? That's, again, we have more questions than answers on that. So if we go beyond Mars, the next group of objects that we have is the asteroid belt. And beyond that are these gas giants. And when I say giants, I mean really, really large. We can compare the Earth in the upper right-hand image here to some of these gas giants. Again, there's 4 of them: Jupiter, Saturn, Uranus, and Neptune. And you can see that the Earth fits about into the red spot here on Jupiter. So which of these is considered a gas giant? Again, it would be Neptune. Lots of other, we got a terrestrial planet and some a moon here and 2 dwarf planets. So Jupiter by far is the biggest non-sun object in our solar system. If Jupiter was a little bit bigger, the gravitational pull would have actually caused it to have some fusion and actually would have been a star. But again, we didn't have enough we didn't have enough mass for Jupiter to become a star, so it's a gas giant. It produces its own internal heat from the compression of all those gases. Those gases are primarily hydrogen and helium. Now, we typically think of hydrogen and helium as exclusively gases, but under the right pressure conditions, you can actually form liquid hydrogen and liquid helium, and eventually these will form a metal under the great forces. Now, we do have convection in the outer portion of the gas giant, where air is rising and sinking down. Just like when we looked at our previous chapter, we looked at Hadley cells with the sunlight most directly hitting the equator, and then that's causing the air to rise and then sink to create these Hadley cells. And so we have bands of air rising, updrafts and downdrafts. We have the exact same thing happening on Jupiter, and as a response, this is going to create these bands or stripes of object of the planet. And so we can see where the air is moving up and back down. One of the most notable things, oops, sorry about that, is on Jupiter is its Great Red Spot. And it's a giant counterclockwise moving storm. And it's been there ever since we've had a telescope to see it. And again, it's as about the size of the Earth, but it is shrinking a little bit. And so I'm not sure exactly why that is, but that's definitely something to be noted. Now Jupiter is very large, and so as a result, it has a large gravitational pull. With a larger gravitational pull, if something comes by it, what's going to happen is it's going to get captured into its gravitational pull and become Jupiter's moon. And Galileo, using his telescope, found 4 moons. In order to buy favor, he actually named these after 4 princes in his in where he grew up. So these are known as the Galilean moons: Io, Europa, Ganymede, and Callisto. And those are, again, those 4 Galilean moons, but they're not the only ones. Now, as these moons are moving past one another, Europa is a kind of an interesting one. So if we start looking at Europa, it's getting pulled by the planet of Jupiter and the other objects, and some of them are closer, and so they get stretched and squeezed. And so when we start looking at Ganymede and Europa, Ganymede and Europa both have liquid water beneath the ice crust. And again, this friction associated with this pulling and stretching actually creates Io to have its own volcanoes, which is another planet moon on Jupiter. But Europa is very interesting because it has 3 things that which make it very, very interesting. First of all, it has all of the different ingredients for life. When we start looking at life on Earth, it's made up of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All of those things are found on Europa. It also has liquid water beneath the crust. It also has tidal forces, which are going to generate some energy, just like when we look at the bottom of the ocean and we see these black smokers. We have all those ingredients. Whenever we find these 3 key ingredients, we have found life. Now, we haven't found life on Europa. We have not been to Europa to potentially find this life, but it's definitely worth noting as if we're looking for other places in our solar system to explore for life, this would be one of them. Europa. So moving on to the next planet, we have Saturn. Saturn is known by its prominent rings. Now, all the outer gas giants do in fact have rings, just not nearly as pronounced as Saturn. Saturn, with the use of a telescope, you can actually, even Galilean's telescope, it looks more elongated, and you really see these rings of Saturn. And again, just like the gas giants are produced mainly of hydrogen and helium, and in this case it's mainly hydrogen. It has the lowest average density. It has no real solid surface. A large number of moonlets always being added to it. It does have a magnetic field and generates more energy than it receives from the sun, again, due to that collisions and the tidal forces, and the fact that it's so far away from the sun. So these rings are very, very unique in that these are prominent rings. Its composition, density, and particle sizes are varied throughout. And so these rings are moving in, these moonlets are moving in very distinct bands, leaving behind gaps in between. And so we've got the Cassini gap right there, and where we actually have a lack of objects in these rings. Now, in addition to those moonlets, those particles forming the rings, we have a large number of moons. Recent results in 2019 say that Saturn has more moons than any other object, any other planet in our solar system. It outpaced Jupiter. We found more of them. Now, one moon in particular is Titan. So again, this is a moon of Saturn. It does have the presence of methane clouds. Maps show hydrocarbons, again, methane and ethane, lakes of active volcanic vents, possibly due to frozen methane gas dunes. Most of the Earth-like objects in the solar system for the number of the type of surface and atmospheric processes occur throughout very cold temperatures. And so we can see one of Saturn's moons, Enceladus, and this was unique in that we saw little jets of water ice promenading from that surface. Our next planet going out is Uranus. And what's unique about Uranus is that it rotates at 98 degrees. So instead of having the Earth rotating like this, it rotates like this. Again, it rolls on its side. It has a high amount of methane, giving it a bluish color. These ice giants have an interior probably made of water ice, H2O ice. Again, the weight of the gravitational pull of the materials most likely creates a rocky metallic core, and its size is very, very similar to its twin, Neptune. And now, Uranus does in fact have a ring. What's unique about this is because it's rotating on its side, you're not going to really see it. It's going to look a little bit larger. How we actually found out it did have a set of rings is that when it passed in front of a star, we made a transit of that star. We saw that the star was being blocked out by the ring. Then we saw the gap where before the planet moved in front of it, and so it almost looked like that star was, quote, winking as a response. Some of the moons of Uranus include Titania, made up of ice and rock here, and the next or the last planet that we're going to be dealing with is another gas giant. Again, the twin of Uranus, which is Neptune. Again, blue color from methane. It has very strong winds, an active atmosphere with bands and some small cirrus clouds there. You can see some thin wispy clouds. And so when we start looking at Neptune, we can see these faint rings. And so all of the gas giants do in fact have rings. One of the moons of Neptune is Triton, which exhibits orbits retrograde, which means it's instead of moving in the counterclockwise fashion like all the other moons that we have, it's moving in the opposite direction. It has relatively few number of craters on its icy surface compared to its bodies, compared to other bodies. And so there's a couple of things that would inhibit the formation of craters. One is we don't have many craters here on Earth because we're washing over and filling in our craters with active weathering taking place. The other thing is it could be a relatively young object in space, and if it's young, it doesn't have much time to build up those number of craters. So those are kind of the two things that would create this few number of craters on the moon, on its moon. So which of the following planets have rings? Jupiter, Neptune, Uranus, and Saturn. So all of the above. So those are our planets. We have just a few other things to talk about in this chapter. The first of which are asteroids. Asteroids are objects that are moving in the same pattern around orbiting the sun in that same area. So if we take a look at the Mars, in the area in between Mars and Jupiter, we can see each one of these objects here are asteroid belt. Now, to fly through an asteroid belt is really stupid. If you just went up a little bit or down a little bit out of that plane of ecliptic, you would have no problem getting around the asteroid belt. But there are two different possibilities as to why we have an asteroid belt. We have planetesimals that never coalesced into large bodies, or they coalesced into large bodies and just didn't have enough gravity to they've since been broken up. Now, the next couple of years will be very interesting because in the last in 2020, we have been going around and we landed on one of these asteroids, and we have gotten some of these pieces of this asteroid, and we have brought it. We're in the process of bringing it back, and so it'll be very interesting to see. Maybe we'll be able to figure out a little bit more about the history and the origin of these asteroids as we're doing that currently. Now, beyond Neptune is this object named Pluto. Now, it was, again, it was discovered on accident. There was a mathematical error that we thought Neptune had an oddity in its orbit associated with the gravitational pull of something. And so there was a big hunt to try to figure out what this was. Well, what this was a math error, and it was a rounding error. And as it turns out, there is not a pull on any other object. Double check your math, kids. And we found that, but in doing so, we were looking for this unknown planet. And so we were looking through the sky for any object that in fact moved oddly compared to the other objects in the sky. Again, created that retrograde motion, moving backwards. And that's exactly what we found in the sky. We saw that this one object moved, a object in the sky, a celestial body, moved different than the rest of its other orbits, other objects in that constellation. And then that's when we found out, we identified this object. It was called Pluto at the same year that Mickey Mouse named its dog Pluto, and that became into Walt Disney's world. But so they both came into existence at the same time. Pluto is the god, by definition, is the god of the underworld. And so it makes a little bit more sense why Pluto was named this object in the sky, on the edges of our solar system, a little more than the dog. But its orbit is also very eccentric, which means that it's very stretched out. We looked at the Earth having a difference between 90 and 93 million miles as it moves around the sun. Well, its orbital plane is tilted at 17 degrees. And again, almost all the other planets are tilted pretty much in alignment with one another. Again, Pluto's orbit is actually elongated. In fact, it's elongated in that it also will move sometimes closer than Neptune. Again, due to this elongated eccentric orbit, the average of the orbit is significantly further away than Neptune. So when I went to school and I learned, my very excellent mother just served us 9 pizzas. The 9 in the pizzas made sense because Neptune was closer than Pluto. And most of the time that's the case, but sometimes due to that eccentric orbit, Pluto is actually in some cases closer than Neptune. Now, having said that, Pluto did not clear out its orbit. And so as a result, since 2006, it's been dubbed a dwarf planet. By definition, it didn't meet the criteria of a planet. So it's located in the Kuiper Belt. And so in 2015, the New Horizons spacecraft flew by and it collected some photographs. Now the upload and processing speed from at the time it was sent off wasn't that great. If any of you are old enough to remember America Online and the amount of bandwidth that you could send through the phone lines, cut that in half, and that's what you have for the data processing and this data sending information back and forth from the New Horizons. And you could either send or receive data. And so there was not a lot of data sent back and forth. Telling it to do something meant it couldn't be doing anything else. It couldn't send any information back. So after we we told the New Horizons spacecraft to take a bunch of photos, do these things. It did these, but we had to wait and see what those images are. And we're talking 20-something minutes of time before any bit of data goes from the New Horizons spacecraft all the way back to the Earth. Even radio waves moving at the speed of light, it takes multiple minutes before you finally get that information. So in 1978, we saw that Pluto did in fact have a moon. We noticed these two objects. We thought it was one large object. We saw now that it's two objects moving around one another due to improved telescopes. It also has a low number of impact craters compared to its surface. Since when we prepared that New Horizons spacecraft, we actually now see that it in fact has two additional moons beyond the Charon. Those are Nix and Hydra. Nix, Hydra, and H. New Horizons. Hey, that's why the New Horizons was named that. So when we start moving beyond when we start moving beyond the Kuiper belt and we go rotate around away from the Kuiper belt, we have this Oort cloud. And in this Oort cloud are highly elliptical orbited materials of comets. And so they're not all in that same plane. Here's an image of Halley's Comet, and we can see that it is not, in fact, in that same orbit. These are traditionally referred to as dirty snowballs, as loosely bound bits of rock and ice. And when they come closer to the Earth, to the sun, what's going to happen is some of that material is going to melt and outgas and leave behind its tail. Now, what that tail is not telling us which direction it's going, it's telling us which direction the sun is. And so the sun would be beneath us from this vantage point. And so here's an image of the comet with the coma being shown here, and the tail behind is that ion stream of gases. And so you can see the sun must be on the right side of this image because it is where the escaping volatiles are occurring. And so, again, the ion points away from the sun at all times. The dust trail slightly curves, but it's still away from the sun. And again, the ions are charged gases that have a positive or a negative charge. That's what we mean by an ion tail. If it's a particulate matter, then we'll call it a dust. And so we can see that those two tails are found. This is the image of the Hale-Bopp comet. Now, again, when I started this chapter, I mentioned meteors, meteorites, and meteoroids. A meteoroid is an object in space whose path crosses the Earth's orbit and may, in fact, ultimately collide with the Earth. Most of these objects are small, a meter across or less. And if they make their way into the Earth's atmosphere, they're going to cause friction with the atmosphere, and it's going to cause immense heat. And most of the time, these are going to vaporize as they enter the Earth's atmosphere to create a large shock. these are sometimes called bolides. As they move across the sky, they're going to leave a strong light. Now, if you do see one of these lights, get down and get away from the glass. I know it would be really a cool thing to see, but what's going to happen as that friction is causing that air to heat up, just like thunder, it's going to create a sonic boom. And so what's going to happen is that air is going to expand and move out, and it will shock that air expanding, moving out will actually break glass. So if you see something like this, get away from the glass. Um, this was an image that had a meteorite entering a meteor as it's entering into the atmosphere, hitting, heating up the air, creating this large boom, and ultimately breaking a lot of glass. Now, if you think you have a meteor, which can occur during a meteor shower, these objects can hit the Earth, and when they do, they become a meteorite by definition. If we slice these open, since these are pieces of materials from, if these are pieces of material, all right, so when we start having a meteorite, if you find a meteorite, one of the things that you're going to notice about it is going to have, going through the atmosphere, they're going to have this cooked, baked appearance on the outside. And it's called a fuselage crust. And so you can actually see that. If you were to slice this meteorite in half, you would in fact see this very common pattern. Before you even go through the effort to try to cut these in half, one of the things that you want to do is double check to make sure that there is iron. If these are materials from our solar system, a lot of these rocky materials, just like our Earth, would primarily be iron and nickel. And so it would react with a magnet. It would attach, you'd feel this magnet. And so you pick it up, it has a high density, it has that fuselage crust, it reacts with the magnet, then then there's a really good chance that you have a meteorite. And they have been found in this area. One of the things that you would do would be to go down and look at the area that was hit, and they're going to hit with such force. What's going to happen is they're going to metamorphose the rocks around them to have what's called a shocked quartz. And so there have been meteorites found in this area. If you think you've found a meteorite, Washington University has a great website that actually kind of gives you a walkthrough to figure out if you find those meteorites. But most of the time, we're not going to find the meteorites because they're going to burn up in the atmosphere. But if you want to see a meteorite or see a meteor shower, I would recommend different times of the year to look in the different parts of the sky. Now, as the Earth moves in its orbit around the sun, there are times that it comes in contact with a lot more of these particulates that we're running through basically a region that has a region in space that would have more of these objects. And so if we go through that region, what we're going to end up doing is exhibiting a meteor shower. And there, again, since the sky has, we can look at these different constellations, talking about different areas of the sky. These meteor showers are named from the constellation which you see them coming from. So we have the Leonoids and the Perseoids. Again, those are different meteor showers. And a meteor shower is just an observer would typically have an increased chance of seeing meteors from hundreds of meteors an hour at the top here. And we can see it in that image. So when we start looking at the Earth or the solar system as a whole, where's the edge of it? And so when we start looking at the edge of their solar system, that's technically called the heliosphere, sun sphere, the region affected by our solar wind. And so if we start looking at the Kuiper belt there, we can see that's that belt where Pluto is located and all those other objects. Going out a little bit further, we have that's heliosphere, that region affected by our solar winds. And this extends in multiple directions, in all directions, to create a sphere, and that sphere is called the Oort cloud. And again, thousands, 100,000 astronomical units. Again, an astronomical unit is the distance from the Earth to the sun. So if you have any questions about this chapter, be sure to let me know. Have a great day.